Hi Bobcats. In this video, we're going to take a look at how to write the expressions for an equilibrium constant. A couple of things to keep in mind. First of all, when we write these equilibrium constants, it's going to be a capital K, unlike the lowercase k in the rate constant for the previous chapter. And the second thing to keep in mind is when we start solving equilibrium problems, such as problems that use ice charts later on in the chapter, one of the very first things you should do is write out this equilibrium constant expression. I've watched so many students over the years set up all sorts of stuff beautifully, and then they just skip to throwing numbers into their calculator without actually writing out the expression, and they'll forget exponents when they do that. So it's so important that you write out the equilibrium constant expression before you start solving any problems involving equilibrium. Our objective is to determine these equilibrium expressions and the constants. Here's how we begin to write these equilibrium constant expressions. For this reaction, 2NO2 in equilibrium with N2O4, the equilibrium constant expression is the concentration of N2O4 divided by the concentration of NO2 squared. Let's look at another example. Oh, yes, definitely want to point out that's a capital K. In our next example, we have 2NO plus chlorine in equilibrium with 2NoCl. The equilibrium constant expression is NoCl squared divided by NO squared and Cl2. And for our third example, we have this process for creating ammonia. Nitrogen plus 3 hydrogens are in equilibrium with 2 NH3, and the equilibrium constant expression says ammonia squared divided by nitrogen and divided by hydrogen cubed. I want you to pause this video and take a moment and see if you can figure out what the pattern is. How do we go from the balanced chemical equation to an equilibrium constant expression? Okay, pause it now. All right. Hopefully you figured this out. What we're doing is we are taking the products and putting the products into the numerator. We are taking the reactants and putting the reactants into the denominator. And then if there's a coefficient other than 1, that coefficient becomes the exponent. So just kind of generically speaking, an equilibrium constant is going to be products raised to the coefficients divided by reactants raised to the coefficients. If you have more than one reactant or more than one product, you just keep multiplying them in the equilibrium constant expression, and you just keep pulling their coefficients to be the exponents on those terms. And remember that the square brackets means the concentration in molarity. Let's look at a few more examples to make sure we've got this down pat. And we're going to look at heterogeneous equilibrium, heterogeneous in terms of phases. We're going to have mixtures of solids, liquids, gases, aqueous solutions. Let's see what happens now. If we have PbCl2 solid in equilibrium with lead ions and chloride ions, our equilibrium constant is Pb plus 2 times Cl minus squared. That's interesting. The reactant didn't appear in this one. For our next example, we have calcium carbonate solid in equilibrium with calcium oxide solid plus CO2 gas, and K is equal to the concentration of CO2. We're missing a couple of terms in this one. And last but not least, calcium oxide plus carbon dioxide in equilibrium with calcium carbonate. K is 1 over the molarity of CO2. So yeah, that third one is just the same thing as the second one, it's just reversed. Something different is going on here. Pause this video for a moment and figure out what's missing and what's present. All right, hopefully you figured this one out. I'm sure you did, actually. What's missing are all of the solids. And it turns out that the concentration, I shouldn't circle the one that's a gas when I'm looking for all the solids. The concentration of a solid doesn't change significantly, so it's effectively a constant. So we just don't write that. You can think of it as getting wrapped up into the value of K anyway. So pure solids we don't write in our expressions, and pure liquids we don't write either. What will appear in our equilibrium constant expression will be the concentrations for gases and for aqueous solutions. So we're going to write into our expression anything that's aqueous or a gas, and we're going to omit anything that's a solid or a pure liquid. All right, let's bring together those last several slides. When we are writing our equilibrium constant expressions, make sure you write it right at the beginning every time you're working an equilibrium problem. We're going to put products over reactants. We're going to use the coefficients as exponents, and we're going to include anything that's aqueous or gaseous, and we're going to omit all solids and pure liquids. Let's practice writing some of these K expressions. Feel free to pause this now and write it, and then come back and I'll show you how I would write the expressions. All right, here we go. For our first reaction, we're going to take products over reactants. In this case, all of the chemicals are gas phase, so they will all appear in our expression. So in the numerator, we're going to put N2O and NO2. They both have coefficients of 1, so we don't write any exponents since it's an understood 1. In the denominator, we're going to place NO. And NO has a coefficient of 3, so we're going to put a cubed for the exponent in the denominator. For our next one, aqueous HF in equilibrium with H+ ions and fluoride ions, K is going to be products over reactants. Everybody is aqueous, so everybody will appear in the expression. So in the numerator, we're going to have H+ ions multiplied by F- ions. And in the denominator, we're going to have HF molecules. And last but not least, down here with silver chloride in equilibrium with silver ions and chloride ions, the aqueous species will be in our expression, but the solid will not be. So we're going to leave this guy out of our expression. Just to make sure you keep things in the right spot, numerator or denominator, I strongly recommend that anything you're leaving out, you put in just a 1 for it and then simplify your expression. So here's what I mean by that. We're going to have products over reactants. So we're going to have silver ions up top and chloride ions up top. And then in the bottom, we would have silver chloride, but we're not going to put it in, so we'll just put 1 in as a placeholder. And when we simplify that down, we'll have silver ions multiplied by chloride ions. That probably wasn't really critical for this particular reaction, but if we'd had the reverse of this reaction, putting that 1 in there helps you keep things in the right spot, because if this reaction were reversed, the equilibrium constant expression would be 1 over silver ions and chloride ions. Let's take a look at some actual numbers for an equilibrium constant. When we are looking at this data table, I want to kind of draw a divider here in the middle of the data table. Everything before my purple squiggly line is how we set up the experiment. Those are initial conditions, so it's saying what it is we put initially into the flask to make this reaction take place. And then the everything past the squiggly is what concentrations have been measured after this reaction has reached equilibrium. So the chemical reaction we are looking at is N2O4 in equilibrium with 2 NO2s. In experiment 1, 2, and 3, we're starting off this reaction by putting varying amounts of NO2 into our flask. And so yeah, I know that seems a little bit weird. We're starting the reaction by putting products into the flask. This is the thing that happens with equilibrium. You can start with reactants or you can start with products, and you're still going to end up with this equilibrium mixture of both. So in this particular set of experiments, 3 of them start by putting what we're writing as the product in the flask to begin with, and only the last one starts by putting what we're writing as the reactant into the flask to begin with. But because these reactions go in both directions, we're going to end up at equilibrium no matter what we start with in that flask, whether it's pure reactant, pure product, or a mixture of reactants and products. Okay, based on writing the chemical equation this way, we can come up with an equilibrium constant expression that says NO2 squared divided by N2O4. If we take the data from experiment number 1, once it has reached equilibrium, because when we write these equilibrium constant expressions, it is so important that the only numbers that go into them are the numbers at equilibrium. So we'll take the equilibrium data from experiment number 1. For NO2, we have a concentration of 0.0172. That goes in the numerator and gets squared. For N2O4 at equilibrium, we have a concentration of 0.00140. That goes into the denominator. And if you run that through your calculator, you end up with 0.211. Now, I'd like for you to run this calculation and get a number for K for experiments 2, 3, and 4. Pause this video, run those numbers through your calculator, and then start up again. Great, now that you have those numbers, let's see if you got the same thing that I did. So I already showed you here for the first experiment, we get a value of 0.211. Now when I ran the numbers for the second experiment, I also got 0.211. For the third experiment, I got 0.213, and for that last experiment, I got 0.213 as well. These numbers are essentially the same. They differ by 2 in the last significant figure, so these numbers are essentially the same number, and this is what we mean by K being a constant. It doesn't matter what set of conditions we start with. Once this reaction has reached equilibrium, this process of squaring NO2 and dividing by N2O4 gives us the same number. Our objective was to determine how to write these equilibrium constant expressions and to actually get some numbers for a constant. Remember, as you write your equilibrium constant expression, it's going to be products over reactants, and we'll raise both of them to the powers of their coefficients. And if you have more than one reactant or more than one product, you just keep multiplying by all of the reactants in this way and all of the products in this way.